The last video for directional derivatives is going to be a short proof and then an example after. Okay, so this theorem actually just kind of formalizes what we saw in the last theorem about level sets. So if we have a function and it's has continuous first derivatives, so that we can do the gradient and whatnot, then what we can say, and I forgot a period there, if we have x naught as a vector, so a vector or a point, and all this is saying is that it is on the level sets. Okay, so this is the level sets. Okay, then all we have to say is that the gradient, right, is perpendicular to s, which this really just means, or rather the line or plane tangent to s, so tangent to our surface. Okay, so just as a idea, so this is just that the gradient is perpendicular to level sets. Okay, and if we visualize this, just drawing some random curve here, okay, something like that, and we're going to call this the level set f of xy is equal to c. And if I have a point here, let's say that that's our point, this is x naught, and then we're going to see eventually that if I look at these two vectors, okay, this is going to be a right angle, this should be my gradient vector, and this other one is going to be another vector, which I will label soon. Okay, I am going to do a proof. It's going to be short, just for 2 dimensions, and then you can extend it. But what we're going to do is we're going to start with some x naught in the set of all vectors x, such that f of vector x is equal to c. Okay, and then with this we're going to parameterize. Actually, parameterize as x of t, okay, and then consequently we would say that x naught is x of t naught, okay, and then by definition we have that f of x of t is equal to c, right? And that's just our level set definition. Okay, and then if we differentiate both sides, so I'm going to take a time derivative with respect to each side, okay, d dt, and I end up with f prime, which I can also represent as a gradient of f of x of t. Okay, and I think I'm forgetting vector arrows here. Let's do vector arrows on x. And then I have dotted with vector x prime of t is equal to 0. Oh, so that means the gradient vector is perpendicular to the derivative vector. Okay, so that's what this vector should be here. And then here, this is essentially the proof. We just need to insert t naught instead of t, and so we've shown that the direction vector, or the gradient vector, sorry, the gradient vector is perpendicular to a line or a tangent, a line or a plane tangent to our surface. In this case, we did a line because we had 2 dimensions. Okay, so nice proof, or outline of a proof. Okay, there would be things you'd have to add in a formal proof, but let's see if we can apply that idea here. Okay, so we want to find the equation of a tangent plane to that thing. Oh, that's fun. Okay, well, oops. Alright, so if I just rewrite this, let's maybe just write it out as x to the fourth, and then, let's see, I'm moving everything over to one side, x to the fourth, it'd be negative x to the fourth, and then plus x squared minus y squared plus z squared is equal to 0. Okay, but how does that help us? Okay, the previous one said, well, I need to write this as a level surface, right? If I wanted to find a tangent plane. Okay, well, the thing is that I need it to look like a level set, right? Well, I think I have a level set, right? So this is my value of c, in quotes, and this is my function f. Okay, so what I can do is find the gradient of f, or what I'm calling f, which I believe here is, and if I do this, okay, is minus 4x cubed plus 2x, right? And then I have y as minus 2y, and the z component is just going to be 2z, okay? And with this, I know that this is going to be a normal vector, right? It's perpendicular to the tangent plane. Okay, so let's see, and then at our point 0, 1, minus 1, I end up just getting 0, and then 2, negative 2, and negative 2. Okay, and so now this is my normal vector to a plane. Okay, and then we have to go back to Calc 2 and remember that, okay, well, if I'm finding the equation of a tangent plane, right, I can use that normal form, which is my normal vector dotted with a vector on the plane minus a point on the plane. Yep, I think I actually want that in parentheses, is equal to 0. Okay, so then really all my answer here is going to be is that I have the vector 2 or 0, minus 2, minus 2, dotted with, and then I have the vector x, y, z, minus 0, 1, minus 1, and that is equal to 0. And that's actually going to be my answer. Yes, I can expand it if you feel so motivated. Feel free to on your own time. Okay? And so that's just a nice, useful property of how the directional derivative and the gradient and all that stuff is going to help us find equations of tangent planes. Alright, and that's going to conclude the videos for this week.